if you could just, to jog our memory, let's write down friction equals mu times the normal force. This is how we defined the force of friction. You got it okay, Ty?
Yeah, I think so.
You think so? It says less than 5 on the front?
No, it doesn't. Yeah, let me tell you this.
All right. It says for each of the blocks below, write a vertical force equation, find the force of friction, write a horizontal force equation, find the acceleration. You know what? Let's go like draw a line right down the middle of the page, and we'll do the left-hand block on the left-hand side, the right-hand block on the right-hand side, and we can see how they compare. And let's do a free body diagram for each of these. Although, let's get lazy. Derek, instead of rewriting everything, did they give me a picture of each mass? I'm going to label the forces on each mass. You ready, Derek? What are the forces acting on the left-hand mass? Get the obvious one. I agree. What else? Which way? Friction acts up? I don't think so. Because which way are we pulling this thing? To the? See the 20 newtons to the right? Okay. By the way, we're going to give this one a name. We're going to call it the applied force. When I talk about the applied force, that's the person off of the screen who's pulling whatever we're talking about here. Okay. Which way did you say friction was? Okay. And I'm pretty sure it's going to be shorter than the 20 arrow because I'm pretty sure this is going to be sliding to the right. What else? Ah, bigger, smaller, or the same size as mg? Okay. You okay with me there? All right. Let's do A together. It says, write a vertical force equation. What did you say about the normal force and mg? They are the? You know what? There's my vertical force equation already. mg, well, let's do it this way. Fn equals mg. B. What does B want me to find, Derek? Friction equals mu times the normal force. I don't know the normal force. Oh, but look, 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 look. I know another force the same size as the normal force. Which force? mg. So I think I can say it's actually going to end up being mu mg. Do I know mu? What's mu? I don't know. What's mu with you? Oh, in the picture, what's mu? 0.12. See it? Do I know m? Do I know g? Yeah. Plug and chug time now. So I can safely say friction is going to be 0.12 times 10 times 9.8. I think I can do this in my head. 10 times 9.8 is going to be 98. 98 times 0.12, it's going to be 9.8 plus 1.96. It's going to be 10.8. It's going to be 11.76. Yeah? Derek, 11.76 what? Because it's a force. I'm going to pause. I want to compare that with the other one, the one on the right. Ready, Ethan? On the right, what are the forces acting on this mass? Get the obvious one. I totally agree. What else? Bigger, smaller, or the same size as mg? I disagree. It's the same mass, so mg is still going to be 10 times 9.8. What's different about this diagram than the other diagram? 15, pushing which way? So is the normal force going to be bigger, smaller, or the same size as mg? No. Is this mass sinking into the ground like quicksand? Is this mass sinking into the ground like quicksand? Is it flying at you like Superman? So everything down has to cancel out everything up. What do I have down? Two forces, yes? So the normal force is actually going to be larger. You with me there? What else? Which way is the applied force? To the? So which way is friction acting? To the? You okay with that? Okay. Can you give me a vertical force equation? Can you tell me which forces, plural, have to cancel each other out? I'm sorry, I can't hear you. No. You're overcomplicating it. Is it sinking into the ground like quicksand? Say no. Is it flying through like Superman? Say no. So ready? Is it sinking into the ground like quicksand? Is it flying through like Superman? Then things must be balanced. Everything up has to equal everything down. Everything up has to equal everything down. Okay? And you were missing that 15. We've got to include that 15 in our vertical force equation somehow. By the way, look up. Really, don't write this down. What I did was this. Winner minus loser minus loser. But I know it has to equal 0 because A is 0. And can you see I plus the mg over and I plus the 15 over? But then I said, hey, wait a minute. How about everything up equals everything down because it's not accelerating vertically? You okay with that? Okay. Redeem yourself. What does part B want me to find? Friction equals what times what? I don't know the normal force. Oh, but look. I know some other forces the same size as the normal force. My equation is going to end up being mu bracket mg plus 15. Is that okay, kiddo? It's going to end up being, what's mu? I don't know. What's mu with you? No. 0.12 times 10 times 9.8 plus 15. Hear that one in your head, Mr. Do? Well, maybe. 10 times 9.8 is 98 plus 15 is 113. 0.12 times 113 is going to be 11.3 plus 2.26, 13.3, 13.56. Yeah? Woohoo! Newtons. Ethan, you okay with where that vertical equation came from? Where the A equation came from? Do you see you're overcomplicating it? Yeah? Okay. Derek, coming back now to the previous one. Part C. What does part C want me to find? Oh, horizontal. This way? Who's winning? Which way do you think this is sliding? To the left or to the right? Who's winning? To the right. Which force is that? Yeah. Oh, you even gave me the physics term. Sure. F applied. Who's losing? Yes. What does that always equal? MA. Ethan, can you give me the horizontal force equation for yours? Who's winning? Who's losing? What does that always equal? It's the same equation as Derek. The difference is your friction is going to be different because there was an additional, the normal force was different. Is that okay? The applied minus friction equals MA. Derek, what did part D want me to find? Oh, how would I get the A by itself in this equation? Oh, so if I hear you correctly, you're telling me that the F applied would just drop down like a domino, and the friction would just drop down like a domino, and it would be divide M? Have we got the A by itself? Let's plug and chug. What is the applied force in this question, Derek, my friend? Minus, how big was your force of friction? 11 point divided by, what's the mass? You know what? I should be able to do this in my head, because 20 take away 11 is 9, take away 0.7 is 8.3, take away 6 is 8.24, divide by 10, 0.824? No? 0.824? That's what I said. Isn't it? Is that it? No? By the way, you better be able to do this on your calculator. Is there more than one number on the top? Yeah? Put the top in brackets. Some of you might want to get your calculators out. Not that I'm mentioning any names. Is it 0.824? Yes? And it's an acceleration, so meters per second squared. Ethan, what do they want me to find in part D for you? How would I get the A by itself? Do you notice we're getting the same generic equation? What's changing at the very top is the normal force, and that is going to domino all the way through and give us a different answer all the way through. But can you see the approach is going to be very similar? Is that what you're saying, me? What was your applied force, Ethan? 20 minus, how big was your force of friction? And the mass was still 10? Oh, I could do this one in my head because it's 20 take away 13 is 7, take away 0.5 is 6.5, take away 6.44? I'm pretty sure on that one. Double check me, though. Yeah? I like those questions. I like those questions. I like those questions. Okay? Before we pause, do you see, Ty, how we generated this little equation right here? Okay, what else can I do? How can I mix and match? Cam, it seems to me I could give you this same question, but I could tell you the acceleration and say, find how big the applied force was. In other words, I wouldn't give you that number. I'd say, oh, if it's accelerating at 3.6 meters per second squared, how hard are we pulling? In many ways, that's easier. How would you get the applied force by itself in this equation here? Add friction over. No dividing. Okay. What else could I do? I could, if I wanted to, give you the applied force, give you the acceleration, and say, hey, what's mu? I don't know, what's mu with you? No, hey, what's... Oh, let's talk about that. Turn the page. There's actually two types of friction. There can be friction on an object even when it's at rest because the hills and valleys will lock up even when we apply a small force to an object. There's sliding friction and there's getting it moving friction. How many of you have ever tried to slide something? Is it easier to get it moving or is it easier to keep it moving once you get it sliding? Keep it moving. So it's actually, turns out, Kareem, there's two mu's. There's the mu once you get it moving, which is smaller. There's the mu to get it started, which is bigger. So the force of friction on an object at rest is called static friction, because static means not moving or unchanging. You ready, Sam? Long blink. If we pull on a desk with a force of 2 newtons, and the desk does not move, then which of the following is true? A, static friction is greater than 2 newtons. B, static friction is exactly 2 newtons. C, static friction is less than 2 newtons. Or D, there is no static friction. You know what? Since there's 4 choices, this is a chance for us to vote. Once again, how high you hold your hand up is how sure you are of the answer. So, here's the example. I'm going to pull on this desk here with 2 newtons, and it doesn't move. What is correct? A, B, C, or D? Or, heck, I'll pull on this desk with 2 newtons, and it doesn't move. What is correct? A, B, C, or D? Who says, it's got to be A. A. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13. Who says, it's got to be B, Mr. Duke? 1, 2, 3, 4, 5, 6, 7, 8, 9. Cam jammed his hand up. He's pretty confident. It's got to be C, Mr. Duke. C, I say C. D, Mr. Dewick. Got to be D. So I'm adding it up to 22, and I got 29 people here. So I got 7 of you that are cowards. Convince me. Cam, you shot your hand up pretty confidently. Were you confident? You know what? I'll let you off the hook, Cam. You're correct. Why are you correct? If static friction was greater, if I'm pulling with 2, but static friction is 5, what must this desk do? It's got to be accelerating that way. Okay. Friction is as big as it needs to be until it reaches its maximum. Okay? In fact, if you want me to explain this, how about you could just write down Newton's first, and if that's enough for you, Cam, you could write that down. For the rest of you, if you want a longer explanation, Newton's first says, well, if the desk isn't accelerating, the forces have to be balanced. They have to be balanced. Otherwise, it would be accelerating. Are you seeing why I said Newton's first is such a powerful law? Really, it explains an awful lot about why things behave the way they do. Static friction acts when you have 2 objects at rest relative to each other. For example, static friction is what keeps a car at rest on a hill when you apply the emergency brake or the parking brake. Static friction is what would anything that's resting on a hill. Static friction is what's holding it on a hill. Okay? The force required to overcome static friction is always bigger than the force needed to balance sliding friction. Or, as you may have discovered if you've ever tried to move furniture, getting something moving is a lot tougher than keeping it moving. Getting something to slide is tough. Keeping it sliding is pretty easy. Okay. And I think I said to you, in the next 8 years or so, you will probably help a dozen or so of your friends move in exchange for them helping you move. It's the big pizza giveaway. It's all part of growing up as a young adult when you move out once and relocate once or twice before you settle down. Okay? We think that the reason static friction is bigger is because the objects have settled into those valleys and you have to break the bond. Or, you know what, I'll give you another way. If you've ever been on a bumpy gravel road, do you notice the bumps more going really slowly or going fairly quick? Really? I find if I go in a 4x4 fairly quick, the wheels don't have time to sink down into every single puddle. They kind of they're still in free fall. They skim over it's bumpy, but if I want to experience every single bump, if I go walking speed in a 4x4, I will feel every single bump in the road. I think it's something similar for static versus kinetic friction. When you get the object sliding, it doesn't have time to settle into all those nooks and valleys and hills and valleys. It skims over them a little bit. But when you come to a stop, it settles into them all. It's actually more complicated than that, but that works. Having said that, Jaden, to keep the math nice, we're going to treat both types of friction as the same thing. Okay? So, friction equals mu times the normal force. Where mu is called the coefficient of friction. And where do we get the normal force from? Ethan, we get it from a free body diagram. I will never give you an equation for the normal force. I don't know that there is such a thing. What I can say to you is, look. You'll know other forces the same size as the normal force because the object isn't sinking into the ground like quicksand or isn't flying into you like Superman. Or in the elevator question, we'll do winner minus loser to find the normal, so we can calculate it. Put your pencils down, look up. Here are some fairly common coefficients of friction. Tyler, here are some fairly common mu's on the next page. Wood on wood has a mu of about 0.25. Steel on steel has a mu of about 0.5. We can lower mu by adding oil. So if you lubricate the steel, you can get it down to about 0.1. Can't get it down to 0. Oh, and also you should know friction generates heat. That's why moving machines, moving engines, they generate so much heat. The lower you can reduce friction to, the more efficient they'll be, James, because they'll generate less heat. Rubber on dry asphalt, anywhere from 0.4 to, honestly, till about 0.75, give or take. Depends on how dry the asphalt. Hot day, the pavement is stickier. There's other factors in play. Rubber on wet asphalt, the point is when you're driving in the rain, your force of friction, your ability to stop and corner cam goes down by half. It has nothing to do with your skill level. It's just physics. Slow down. In the rain, slow down. Rubber on ice, steel on ice. These values are approximate, but just to give you an idea, Braden, of what's a really big mu and what's a small mu. Can you have a coefficient of friction greater than 1? Glue would, because it can hold its own weight and then some. I mean, glue, it's actually an adhesive force, not so much friction, but you can kind of think about that. Or expensive dragster tires, race car tires, those have coefficients of friction bigger than 1, because I've tried to convince you, Hannah, that the force that makes the car go forward is friction. If you want to accelerate faster, you need a bigger friction force. You don't want to change the mass of the car. We can change mu. Example 7, I like example 7, I like example 7. Example 7 is nice friction. Says this: a force of 120 newtons is needed to push a box along a level road at a steady speed. You know what? I think I'm going to underline the word steady speed. If the force of gravity on the box is 250 newtons, A, what's the force of friction between the box and the road? And B, what's the coefficient of kinetic friction between the box and the road? This is a job for a free body diagram. Here's the box. Cam, what are the forces acting on this box? Get the obvious one. I totally agree. Is this box sinking into the ground like quicksand? Is it flying here like Superman? So what else? Normal force, bigger, smaller, or the same size? Well, when I read the question, I don't see any hint of other vertical forces, so I think we can say same size. What else? Well, it says that we're pushing. How hard are we pushing? So I'm going to go F applied equals 120 newtons. What else? Which way? Bigger, smaller, or the same size as 120? Why same size in this unusual case? Steady speed. Okay? If I hadn't said that, I would totally agree with you. But the fact that it says that, I can actually say friction also equals 120 newtons. Steady speed. Okay. Oh, what did part A want me to find, Cam? I already know the answer. What did I say the force of friction was? Okay. In other words, I didn't actually go mu times the normal force. I got it from the free body diagram. Natalie, is that okay? Natalie, what's B want me to find? The coefficient of friction. Hey, you know what? Natalie, what's mu? I don't know. What's mu with you? It wants me to find mu. That's what the coefficient of friction is. I put the word kinetic in because I did say there's technically two types of friction, but I'm just going to pretend they're the same, okay? But I had to be fussy as a physics nerd and put it in there. So it wants me to find this. What's the equation that has this in it? I'll give you a hint. It starts like this. Friction equals, you got it on the previous page, Nat, right here? Read it to me. Times the, say it loud and proud, friction equals, you're going to say it again, right? What is it? Friction equals? What did you say they're asking me to find in part B? Okay, so you ready? How would I get the mu by itself? What's the normal force doing to the mu? Adding, subtracting, multiplying, or dividing? So how will I move the normal force over? So if I hear you correctly, and I think I do, you're telling me mu equals friction divided by the normal force, yes? Okay. Get the questions off someone else. I'm going to go over another 30 seconds. I'm not quite going to finish the lesson. Coming back to you, Cam. Do I know how big friction is?
Yeah.
What?
120 newtons.
I don't know the normal force. Oh, but look. I know another force the same size as the normal force. Which, huh? So I can say 120 over mg. Did they give me the force of gravity? No, that's an acceleration, not a force. Read the question carefully.
120.
I don't think so. Huh? They gave me, and I gave it to you, by the way, in newtons. I actually gave you mg. The mass is not 250. The mg is 250. In other words, what's mu? I don't know. What's mu with you? Sam, what'd you get? 0.48? 0.48 what? What are the units for the coefficient of friction? It's a trick question. Rob? There is none. There is none. And I'll prove it to you. This is newtons divided by newtons. What happens when you go newtons divided by newtons? They cancel. Nothing left. Okay? It doesn't have any units. Looks like I'm spending 3 days on this. Yeah. For now, number 1 is the question that I just did with you. You can try that. Try number 2. I'm going to eventually assign number 3, but for, well, you know what? You can try number 1, 2, 3, and 4. There's a good start. I'll give you a bunch more in a bit. Lots of me talking, sorry. Well, the video was cool.